All right, hello everyone. This is the second part of the video for section 1.5. So we'll be continuing on with the material from this section. And we're going to go back now and talk a little bit more about vertical and horizontal shifts. And we looked at these with graphs, but I now want to look at them with tables. And so here's what we got going on here is in this table, we have a set of inputs and outputs for the function f of x, which we don't have a formula for it. All we have are these input and output values. And then we're told to create a new function called g of x, which is given by taking f of x, and recall that this f of x stands for outputs, and subtracting 3. Now, what I want us to focus in on here is that minus 3 there is on the outside of the function, right? So it's f of x, that function, minus 3. So if it's an outside subtraction, recall that that's going to affect the outputs of the function, right? And so when we go to create a table now for g of x, so it's going to be x and g of x here. Okay. Well, again, that minus 3 on the outside only impacts the outputs. So recall that it's not going to change the inputs. So these are going to say is 2, 4, 6, and 8. And another way to think about that is that remember that subtraction on the outside of a function we saw moves the function up or down the vertical axis. So it doesn't change the things along the horizontal axis, which are the inputs. It only changes things on the vertical axis, which are the outputs. And then also because that minus 3 is on the outside, is negative is what I meant to say. Then we saw that minuses like that move things down. So in order to find our new outputs, we just need to go through and subtract 3 from each of these values here. So we do 1 minus 3, which give us negative 2. 3 minus 3, which would give us 0. 7 minus 3, which is 4. And 11 minus 3, which is 8. So our new set of our table for the function g of x would be inputs of 2, 4, 6, 8, and outputs of negative 2, 0, 4, and 8. And if you want to kind of visualize what's going on here, one way to do it is to draw the graph, draw one of the points. So I'm going to draw the point 2, 1, right? So that's our first one there, 2, 1. And then again, remember that a subtraction of 3 on the outside moves this point down 3 spots, right? And so if it's at 1 here, it's going to go down 1, 2, 3. And the new point will be at 2, negative 2, which is what we see over here, right? So notice the input didn't change, but the outputs did. All right? Okay. Now let's look at what happens if we have that minus 3 on the inside. So here now, working with the same function f of x, but now the function g is defined by doing a minus 3 on the inside. And recall that because that minus 3 is on the inside, it's going to now impact the inputs of the function. Okay, which tells us that when we go to create our new table for the function g, the outputs are not going to change. So these are going to still be 1, 3, 7, and 11. But the inputs will change now. And recall or remember, this is on the inside, so it's also part of the house of lies. So even though it's a minus 3, rather than moving things to the left, it's actually going to move things to the right, which means we should do what with each of our inputs here? Right, we should add 3. So that would make this first one here 2 plus 3, which would give us 5. 4 plus 3, which would give us 7. 6 plus 3, which would give us 9. And 8 plus 3, which would give us 11. So our new table for g of x would have the inputs 5, 7, 9, 11, and the outputs 1, 3, 7, 11. And again, if you want to visualize what is going on here, imagine you have, again, that point 2, 1 right here. Okay, well, the minus 3, as we said, does the opposite of what we think. It's the house of lies, so it's actually going to move things to the right 3 spots. So starting from here, we would go over 1, 2, 3. And that would be here, and we'd now be at the point 5, comma 1, okay, which is what we see over here in our table. And you could do that for all the points. Cool? All right. Let's look at some more transformations of functions. And this time we're going to look at what happens when we do numbers on the inside, or we multiply by numbers on the inside or the outside of a function. And so here we're going to be making transformations of the function f of x equals x cubed, which, if you think about, that's another one of our toolkits. Which toolkit is that? Right, that is our cubic toolkit function. So we're going to go back to Desmos here, like we did in the previous video. Okay, and I'm going to input that function. So the f of x equals x cubed. Okay, and just so you know, if you've not used Desmos before, you're trying to do exponents, you can just do your variable and then hit the little caret button that's above the 6 on your keyboard, and then it allows you to input exponents. All right, so first thing we're going to look at is what happens as we put a 2 in the front. So we're going to start with the function x cubed, but then we're going to put a 2 in the front of it. Okay, and what do you see happen there? Well, you know what, actually, I'm going to do this instead. I'm going to make this an A, and Desmos has this nice thing where I can put a slider on that. Okay, so notice now right now we're starting with that value of A being 1. Oops. Okay, we're told here that A equals 1, which means if we plug that in here, 1 times x cubed, we're looking at our function being g of x equals x cubed. And I want you to watch what happens as I now change that value of A. I'm going to increase it. Yeah, I'm going to increase it. So let's watch what happens. And what do you see happening there? Well, it looks like the function is being stretched in the up or down position. So if you notice, I'm going to go back to 1 here again. Watch. It looks like someone is grabbing kind of the top and bottom of the function and pulling them in opposite directions, and it's thinning out the question, but it's the function, but it's also stretching it up or down. Okay. Similarly, let's say we go less than 1 now. So here's 1. What happens now as we move that less than 1? Well, what seems to be happening with the function now? Well, it seems like it's being kind of stretched left to right, but up or down, it looks like it's kind of being squashed, right? As if I was pushing from both the top and the bottom. Yeah, down towards the middle, looks like it's kind of being squashed there, right? Okay, and that one's a little bit harder to see sometimes, but really what it's being squashed, or the word is compressed from the top or the bottom. And notice as we increase the value here, okay, so going from A equals 1 up, first of all, notice that our value for A is on the outside, which means it's impacting our output. So if we look at a particular point, for example, on the original function, this one here, which was 1, 1. Okay, well, if we look at the new corresponding point when A is 3.4, it looks like it's up to here, right? So it kind of got stretched up. If I look at what happens when the value of A went less than 1, okay, so let's say like to 0.5 or yeah, right there, okay. Well, notice here that 0.11 was right here, and it got moved down to here, kind of squashed down, okay. So that's evidence for to kind of explain what is going on here. So here's what we're seeing. So if we have a function f, or a function with any name, we put a multiplier or number out on the front. So that's like k stands for a constant. That's going to cause what is called a vertical stretch or a vertical compression. And notice it says vertical, so that means it's happening along the vertical axis. Okay. And here's how those things get impacted. So if the value of k is greater than 1, then the function gets stretched in a particular value. okay? If the value of k is between 0 and 1, so notice it's not saying negative here, it's just saying value is less than 1, then the graph gets compressed. Okay, and if your value of k is less than 0, so if it's a negative number, then you're going to have a combination of vertical stretches or compressions with a vertical reflection of some sort. Okay, and remember, vertical reflection means across the horizontal axis. And to say a little bit more about those stretches or compressions, okay, they also happen by a factor of k. So what do I mean by that? Well, using the example we were just looking at, we had the original point on our function there, f of x equals x cubed. One of the points on that function was 1, 1. And when we stretch that by a factor of k, of 2, excuse me, so we multiply by 2x cubed, what that then does is, first of all, the 2's on the outside, so it doesn't impact the inputs, it impacts the output. So the input stays as 1, but the output then gets multiplied by that factor of 2, so it becomes 2. So the point 1, 1 on the function f of x equals x cubed got stretched to the point 1, 2. Okay, and again, notice that the multiplier here from 1 to 2 was the value of k, which was 2. Similarly, if we start with that function f of x equals x cubed and the point 1, 1, and we're looking at, if we multiply by a number between 0 and 1, so let's say 1/2. Okay, well, the point 1, 1 is now going to change. Again, the 1 will stay the same, the input change stays the same, but the output now get multiplied by that factor of k, which in this case is 1/2. So notice that the point 1, the output 1 here became 1/2 over here. So that's how that impacts things. Okay, and again, this is when you're multiplying by something on the outside of your function. On the outside of your function. So now let's look at what happens if you multiply by something on the inside of your function. Okay, and I'll tell you as we're looking at these, that some of these transformations are going to look very similar to what happened when we were multiplying by something on the inside, and there are some relations, but the way we think about them are a little bit different. So again, we have that black function there, that's the f of x equals x cubed. Let's look at what happens if we multiply by a 2 on the inside of the function now. Okay, and actually, sorry, I'm not going to do x cubed. I'm going to change this to x squared. Let's see what happens when we multiply by 2 on the inside of the function. So this is going to be a new function. I'll call it g of x equals, on the inside of the function, I'm going to make 2x and square that. And what do you notice happened with that? Well, again, it kind of looks like it was stretched. But because this 2 is on the inside of the function, let's look at what happened along the horizontal axis of the inputs. And notice if I look at, say, this point 1, 1, it looks like it kind of got moved over to this point right here, which was 1/2 1. Okay, so it got squeezed inside. And in fact, let's look again, just like I did in the last one. Let's put a slider on this thing on the inside here. Okay, so here we're at a equals 1, so the two graphs are lining up. And notice is now as I increase that value for a, hopefully you can see the function being horizontally compressed, right? So it's like if someone is pushing from each side and pushing it in. This may look very similar to a vertical stretch, so someone was pulling on the top and bottom, which is true. So be very careful about how this say this. A vertical stretch, so stretching up and down, is the same as a horizontal compression, so as if we were pushing from each side. Similarly, if I go back to 1 here, if we now decrease that value of a, okay, so we're going to go below 1, notice what seems to happen horizontally here. Well, now it looks like someone has grabbed the function from both sides and pulled out in each direction, right? So it looks like for values of a that are less than 1, we see a horizontal stretch. So it's as if we are pulling from each side and pulling in opposite directions. Now again, to connect this to what we were just looking at, that horizontal stretch looks very similar to a vertical compression, right? So stretching horizontally also looks like if we pushed from the top and the bottom towards the middle, then we get this same thing here. Okay. All right, so going back to our PowerPoint to summarize this. So if we have a number now being multiplied on the inside, right, of the function, that causes a horizontal stretch or compression, as it says here. Okay, and in these cases, because it's on the inside and follows the house of lies, it does the opposite of what we would think, right? So notice here when k is greater than 1, so even though it's a number bigger than 1, it actually compresses the graph. If the value of k is between 0 and 1, so a small number, it actually stretches the graph horizontally. And then just like with the vertical stretches or compressions, if the value of k is less than 0, you're going to have some sort of a combination of a horizontal stretch or compression. And this part here where it talks about the factor being 1 over k. Well, notice one way to look at that is when we had the function f of x equals 2x, that whole thing squared. Okay, and we're comparing that to the original function f of x equals x squared. And sorry, this should be a g, not an f. Okay, well in the function f of x equals x squared, we have the 0.11. But we saw that when we put this 2 on the inside, so first of all, it's on the inside, so it impacts the inputs. So the output here would stay as 1, but because it got compressed, right, the input actually became 1/2. So notice to go from 1 to 1/2 here, we had to multiply by the reciprocal of 2, which 2 is the same as 2 over 1, so the reciprocal there gives us 1/2. Okay, so everything got stretched by a factor of 1/2. So it was the reciprocal of what we thought. And again, that's because of the house of lies. All right. Again, I would suggest maybe you go back in the video and rewatch some of this stuff because I know this can be a little bit tricky. All right, thanks for watching. That's the end of this video.